All right, next up is question 6 that says to consider the solid bounded below by the paraboloid z equals x squared plus y squared and above by the plane z equals 4. Find the centroid of this solid using cylindrical coordinates. And I've gone ahead and just sketched a picture of our solid. Here's our paraboloid and the plane. And since we're finding the centroid, the density is constant, right? Uniform density. And so one thing we can say quite nicely at the very beginning is that by symmetry of our solid, and right, you just see how it's positioned in the coordinate system, the center of mass is going to lie along the positive z-axis. So in other words, the x and y coordinates of the center of mass are 0. So that cuts out two integrals we'll have to compute, right, for those the moments about the yz and the xz plane. Okay, so that's quite nice. So let's go ahead now and compute the mass of the solid. So we're going to integrate the density function over our solid E. And since we're integrating over this solid that's bounded below by a paraboloid, it makes sense to use cylindrical coordinates. And so if I let z vary first, so fixing an x and a y, z will vary from the paraboloid, and in cylindrical, x squared plus y squared is r squared, so the height on the paraboloid in cylindrical coordinates would be z equals r squared. So we're going to vary from that paraboloid up to the plane where z is 4. So for the iterated integral, the bounds on z will be from r squared to 4. And then if I project the solid down onto the xy plane, I'm going to get a solid disk here. And the radius of the disk is 2. And the reason why is that this boundary circle here in green is the projection of the curve of intersection between our plane z equals 4 and our paraboloid. And so if I just set 4 equal to z here in the equation of the paraboloid, I get that x squared plus y squared is 4. Hence this disk has radius 2. So these are the bounds then for the disk in polar. And so we can go ahead and compute that integral. Don't forget your factor of r there. For the area element in polar, you need r dr d theta. When you do that integral, you're going to wind up getting k times 8 pi. So that's the mass of the solid. And then as we noted up here, as far as the moments, well, we really just need the moment about the xy plane, which will give us the coordinate of z bar. Okay, so the xy moment there, we're going to integrate z times our density over our solid. So same bounds of integration. We're now integrating kz, and again, remember that factor of r there. When you compute that integral, you end up getting k times 64 pi over 3. And so z bar would be the xy moment divided by the mass. And when you divide these two quantities, you wind up getting 8/3, or in other words, 2 and 2/3. All right, so our centroid's located at the point 0, 0, 8/3. So we're saying we're located 2 and 2/3 up along the positive z-axis. And as we said at the very beginning, yeah, that makes sense, right? So it's certainly a little bit more towards the higher end than the low end. And given that shape, that's what we expected. All right, thanks.